Okay, so now we've got four functions here and we're going to find their domains. So let's start with the first one. We've got a function f and it's defined by the rule f of x is equal to the square root of 3x plus 12. Okay, so, well, are there any restrictions? If so, what are they? And the answer is yes, there is a restriction because look at this. We've got something here. I'm just shading it in. The part that I've shaded, the 3x plus 12, that's all being plugged into a square root. Right? And whenever you plug something into the square root, you know it can't be negative because we cannot take the square root of a negative value. So that's where your domain restriction is coming from. So, and a lot of people will see this example and they'll right away they'll say, okay, oh yeah, square root, right? It's got to be positive or it's got to be non-negative at least. It's got to be greater than or equal to 0. And if you catch yourself saying that, stop and say, okay, what exactly needs to be greater than or equal to 0? What exactly needs to be non-negative? And that otherwise you won't know where to start. But the answer to that question is we need 3x plus 12. Basically, in general, whatever's being plugged into the square root has to be greater than or equal to 0. Okay, and once you get to that point, now the techniques of section 1.2 are going to kick in, right? We've already talked about how to solve linear inequalities. So just do that here, right? Isolate x to simplify this. So first of all, subtract 12 from both sides. That's going to give you this, right? 3x is greater than or equal to negative 12. And then to get the x by itself, divide both sides by 3. So you'll get x is greater than or equal to negative 4. And notice that we had a greater than or equal to sign, and we still have a greater than or equal to sign. I didn't flip the sign when we divided both sides by 3, and the reason is because we divided by a positive, right? If we divided by a negative, we would have had to flip the sign. But since we divided by a positive, you don't flip the sign. Okay, great. So that now we've reduced the inequality. What is the actual domain? Well, you can sketch it if you want. It only takes a second. We got all the values of x that are greater than or equal to negative 4. So to write the domain in interval notation, we'll just say the domain of f is given by the, well, it's going to be half closed, right? You're going to have a square bracket on the negative 4 since we're including that point, and then you'll use infinity as an upper bound since there is no upper bound. Okay, so that's your domain. It's the set of all numbers, all real numbers that are greater than or equal to negative 4. Okay, so what's our next one? We've got this function g defined by, well, g of x is given by the fraction. X minus 4 is the numerator, and then you got a quadratic for the denominator, right? X squared plus 6x minus 7. That's a quadratic. That's actually if you graph it, it's a parabola. We'll talk more about that later in this chapter. But for now, we don't need to go that crazy analyzing it. We just need to look at the fact that, well, hey, there's a fraction here, right? Remember, whenever you have a fraction, that's going to introduce a domain restriction because whatever is on the denominator, in this case, that's x squared plus 6x minus 7, that's your denominator, that cannot be equal to 0. Right? Because fractions really represent division. And if the bottom or the denominator is 0, that would mean you're dividing by 0, but you're not allowed to divide by 0. So for that reason, this is what we need in this case. Right? So you see what I'm suggesting? Start off by identifying what the restriction is before you jump into starting to solve it. Right? And sometimes you're going to have more than one restriction, and it's in your interest to find all the restrictions first before you start to reduce or simplify any of them. So in this case, we need x squared plus 6x minus 7 to be non-zero because it appears as the denominator of a fraction. Okay, well, how are we going to figure out when x squared plus 6x minus 7 is non-zero? This is the way I like to think about it. Just start by figuring out when it is 0, right? So we're going to solve the equation x squared plus 6x minus 7 is equal to 0. It's not that the solutions to this equation are not going to tell you what the domain is. In fact, it's the opposite. They're going to tell you what you want to throw away in order to obtain the domain of G, right? So, but in order to figure out when this is true, we want to start by figuring out when this is true. Okay, so and how do you do that? Well, this is a quadratic equation, right? You've got a couple of options. Probably the simplest case here, the simplest example in this case would be to factor the left-hand side. This actually factors as x minus 7, x plus 1 is equal to 0. Why is that, by the way? Let me include some details up here. If you've forgotten how to factor, here's a reminder. Okay, I'm just going to look at the left-hand side. I'm not going to worry about the equation. I'm just going to say x squared plus 6x minus 7. And we're just going to simplify this expression. So whenever you're trying to factor a quadratic, remember what you're doing. You're looking for two numbers that add to the coefficient of your middle term. So you want them to add to 6, because that's the coefficient of your x term, the middle term. And you want them to multiply, the two numbers to multiply to your constant term, which in this case is negative 7. Okay, so that's where that's coming from. Okay, so what are two numbers that add to positive 6 and multiply to negative 7? The only two options are take negative 7, or pardon me, take positive 7 and negative 1. Right? You can check that they'll positive 7 and negative 1, they will multiply to negative 7 and they will add to positive 6. So take negative, pardon me, 7 and negative 1. So then you can use that to decompose this middle term as x squared plus 7x minus x minus 7. So here's the logic. We had, I'm going to erase this other highlighting. So the logic is we had 6x, right? And we replaced it with 7x minus x, okay? Certainly that's true, right? So if you have 7x and you take one of them away, you're going to have 6 left. So certainly that's true. How did we know to do that? Because of these two numbers here. Because these two numbers are like the key that unlocks this puzzle. Okay, so why does that work? Well, watch what happens. Now we're going to factor these two terms, and then we're going to factor these two terms. And watch what happens. For the first two terms, we can pull out an x. So we're going to have x times x plus 7. And then for the second two terms, well, they both have a negative. We can pull out a negative. So pull out a negative 1, and you'll be left with x plus 7 again. And then now, you actually, this is how you can think of it now. Think of it this way. You've actually got two terms here. Right? The first one is the product of x and x plus 7. The second one is negative 1 times x plus 7. Well, they both have a common factor of x plus 7. So you can pull out the x plus 7, and that's how the factoring is completed. So you pull out the x plus 7. And for the first term, you're just going to be left with the x. So you have x. And then for the second term, you're just going to be left with the negative 1. And that is how that factoring is done. Okay, alternatively to factoring, we could have just taken this and used the quadratic formula, and I'll remind you about that later on. But for now, the factoring works. Okay, so that's a reminder of how to factor. What's the point of this? Well, now, look at this. Look at what we've got. We've got an equation that's of a certain form, right? We've got the product of x minus 7 and x plus 1 is that product has to equal 0. Well, the only way a product of two numbers can be equal to 0, right? If they're supposed to be equal to 0 here, the only way that can happen is if one of the two factors is equal to 0. So this gives you, from this point, you can say that either this factor has to be 0, so x minus 7 has to be 0. Well, when is x minus 7 going to be 0? It's going to be equal to 0 when x is equal to 7. Or the other possibility is that this factor is equal to 0. So x plus 1 is equal to 0. Well, when's that going to happen? X plus 1 is going to be equal to 0 when x itself is equal to negative 1. So that's how you get your two solutions to this equation. So great. Okay, so those are the two values of x that make this equation true, or alternatively, they make this statement false. So to figure out what the domain is, think of it this way. I'll draw the sketch over here. Think of the domain as everything, but we're going to throw away the point negative 1 and 7. So put open dots there and just shade everything else. Okay? Shade everything else. And that is how you get your domain. So now we can say, okay, write it in interval notation. The domain, oops, I didn't leave myself enough room because this is going to be long. So there's 3 pieces. So the domain of G, first we want this piece, so negative infinity to negative 1, union with, then we want this middle piece, negative 1 to 7. And then we're going to need this third piece, which is the set of all points that are greater than 7. So that's going to be union with 7 to infinity. Okay, so that's how we can get our domain written in interval notation. Okay, Great, so we got another one under our belt. So that also gave you a reminder on how a reminder on how to solve a quadratic equation if it factors. Sometimes this method won't work, but then if it does factor, this is a reminder on how to factor. Okay, next one, h. We've got a function h defined by this rule. H of x is the square root of x minus 2, all of that divided by x minus 5. So, okay, we'll start by saying what are the restrictions? What are the restrictions we need to worry about? Well, first of all, we need x minus 2 to be greater than 0. And I'm going to put a 1 here because there's actually a second restriction, isn't there? What's the second restriction? We've got a fraction. So that means whatever's on the denominator, in this case it's x minus 5, cannot be equal to 0. So we need x minus 5 not to be equal to 0. Okay, great. So anything else? Make sure you rule out the possibility of any other restrictions. If there are any other restrictions, you want to write them down now before we start playing around with inequalities and stuff, because that's probably the instinct is to now start playing with this and solving this. But just take a breath, make sure we've got all the restrictions. And we have. There are no other restrictions. Okay, so well, let's start with the inequality. Oops, let's start with the inequality. That one isn't going to take too much effort, right? We just add 2 to both sides, and I'll say equivalent to x is greater than or equal to 2, because that's what you'll get if you add 2 to both sides. Okay, so let's sketch that. So put a 2 here. Now, if I didn't care about this, what would I do? I would draw a solid dot here, and I would sketch this, and then I'd be done. And that would be my domain. However, I'm not going to ignore this. When is x minus 5 equal to 0? When would this fail? Well, when x itself is exactly 5. Right? So we're going to just make one modification here. We're going to throw away the 0.5, but then we're going to keep everything else the same. So we're still going to keep the number 2 and everything greater than 2, except for the fact that we're going to throw away the number 5. And that is going to be our domain for this function. Okay, so in interval notation, what's it going to be? The domain of h is the union of the numbers between 2 and 5, inclusive of 2 but not of 5, union with the numbers that are greater than 5. Okay, so that is our domain. Okay, one more, and then we're done this page, and then actually this section as well. So, okay, so what's going to go on with this function? This is a function named c. What's the definition? It's defined by the rule c of q is equal to 100 times q minus the cube root of q plus 2. So what are the restrictions? I'll give you a minute to think about this. Not quite a minute, but I'll give you a few seconds to think about this. Well, and if you want more time to think, just pause the video before you resume it. But what are the restrictions? Are there any restrictions? Start with the first term. We've got 100 multiplied by q. Well, that's no problem. You can multiply any number by q. Or pardon me, you can multiply any number by 100. So it doesn't matter what q is there. What else do we have? We got q. If I look inside this radical, I have q plus 2. So, okay, add 2 to any number. That's no problem. You can add 2 always. But then we're going to take the cube root, right? We're going to have to take the cube root of whatever q plus 2 ends up being. But remember, cube roots are no problem. Odd roots, in fact, in general, cube roots, fifth roots, seventh roots, anything with an odd root causes no problems, and it introduces no domain restrictions. So again, there's no restriction there. And then subtraction, that's also no problem. There are no restrictions here. So let's just say that. No restrictions. The operations that are used to define this function are defined for all real numbers. So is q. We can say that the domain of c, or not so is q. Q is the input variable. So is c is what I meant to say, because c is the name of the function. So the domain of c is all real numbers. Okay, so that is how you can find domains. Sometimes this function, maybe at first glance, looks like it's fairly complicated, but it turns out it was the simplest of all 3 or all four functions when it comes time to find the domain. Okay, so that's the end of this section. Now you know how to find domains.